Utkarsh, can you start? Utkarsh, are you there?
Hi, am I audible?
Yeah.
So should we start our today's talk?
Yeah, start.
Yeah, hello everybody. So it is my great pleasure to introduce the speaker of today's talk, Professor Shiroman Prakash. Professor Prakash is an assistant professor at the Department of Physics and Computer Science in the Dayalbagh Educational Institute in Agra, Uttar Pradesh. And he did his PhD from the Tata Institute of Fundamental Research, Mumbai, with Professor Sandeep Trivedi. He is an string theorist, and his research area is in a broad topic of in conformal field theory and so on. And so he has many recognition and awards. So he's an DST early career awardee, and he is also an fellow of the Royal Astronomical Society, and he is also a recipient of a Young System Scientist Awardee from the System Society of India, and he was also a visiting fellow of Isaac Newton Institute of Mathematical Science, Cambridge, UK. So we welcome him for his today's talk. So Professor Shiroman, please take the floor.
Okay, so thanks for the introduction. And okay, so the talk here is titled Overview of Dualities. String theory, it's actually, so I don't really work very actively in Calabi Yau manifolds, but from what I thought, okay, from the organizers who invited me, I'll just give sort of a very elementary talk or introductory talk that hopefully gives an overview of what string theory is and a little bit of an idea why there are dualities such as mirror symmetry amongst geometric things coming from string theory, but it'll all be not like too technical or advanced. So hopefully, yeah, for students, it'll be fine. So this is the outline of the talk. So I'll do a quick overview of quantum field theory and string theory. Then I'll talk about 11-dimensional supergravity, which is the low energy limit of M theory. And I'll talk about type 2A string theory and how it comes from 11-dimensional supergravity. Then we'll discuss T-duality and type 2B string theory, and maybe just a few words about mirror symmetry at the end. Okay, and I guess you can interrupt me at any time for questions. Okay, so quick overview of quantum field theory and string theory. So you're hopefully familiar with the two-slit experiment. So in the two-slit experiment, you sum over paths, and to compute the probability amplitude that a particle will be found at a given location on the screen. Let me just put this as a. Okay, is it still visible? Yeah. Okay, so in the two-slit experiment, we sum over paths, and you have to sum over two paths to compute the probability amplitude that a particle will be found at a given location on the screen. If you add screens and slits, then instead of, for example, here you have 3 and 2, so a total of 6 slits and 2 screens, you have to sum over 3 times 2, 6 paths. So if you were to keep this process of increasing your number of screens and increasing the number of slits, you would eventually have to sum over an infinite number of paths. But an infinite number of walls with an infinite number of slits, roughly speaking, is empty space. So even in the absence of any slits, if you want to find the probability amplitude that a particle starting at point A, ends at point B. You have to sum over all paths connecting A and B. And with each path, you associate a phase. And these phases add and interfere to give the probability amplitude that the particle initially at A is detected at B. Okay, and here in this phase, S of x of t is the classical action, which is a functional of the trajectory. And in principle, when h bar is small compared to the action, only those trajectories that extremize the action would contribute significantly to the probability amplitude. And in that sense, you sort of recover classical mechanics. Okay, so this is just quantum mechanics in a nutshell. So when special relativity is combined with quantum mechanics, particles can be created and destroyed thanks to equals mc squared. So in the prototypical experiment, particles collide with each other and they scatter. We don't see what's happening inside, we just see the final outcome, and we want to know what's the probability amplitude for that. So the way we do this is we sum over paths, but we have this added feature that we have to add an interaction vertex, which is this point where the green line and the black lines meet, which allows an electron to absorb or emit a photon. And this interaction vertex can also arise in the sum over paths. Now, you can't just add any interaction vertex, especially if there's the field is a photon. So mathematical consistency restricts the choice of interaction vertices. But it's possible to define theories that is consistent sums over paths for forces such as electromagnetic and nuclear force using a finite number of interaction vertices, but this is impossible for gravity. Okay. And this sum is essentially equivalent to quantum field theory. So it's a sum over field configurations with weights that are some action, which is a functional of a field psi of x of t corresponding to the electron, and a one-form field a mu corresponding to the photon. And of course, there are subtleties in quantum field theory. For example, the field representing the photon is a one form, and only dAf equals dA, where d is the exterior derivative of A is observable, and only mod psi squared are observable. So both psi and A can be multi-valued, leading to subtleties when you consider these fields in spacetimes with non-trivial topologies. Okay, now we come to string theory.
How many components do A sub mu have?
A mu has, well, in this particular example, A mu has 4 components. So that if it's the photon from everyday life.
Is that the space time?
Yeah. So mu runs from, so it has 1 time component and 3 spatial components.
Yes.
So it's mu is an index in space-time. Okay, in higher dimensions, it'll have more indices. Okay, so this would be the quantum field theory of quantum electrodynamics. We have this one form gauge field and a spinor psi sub alpha. Okay, and now what's the difference? So that's just quantum field theory in a very quick nutshell. Now we come to string theory. So what's the difference between string theory and quantum field theory? So a particle traces out a one-dimensional world line in space-time, which is shown on the left, and a string traces out a two-dimensional world sheet in space-time. So that means that quantum mechanics of a string, instead of being a sum over world lines, is a sum over world sheets. That is a sum over two-dimensional surfaces. Okay, and you can also think of this as a quantum field theory because the world sheet is described by a parameterized surface of two coordinates, sigma and tau. So sigma can go along the length of the string, and tau is like a time-like parameter, and x mu are the coordinates of space-time in which the string lives. So you can think of a sum over paths for a world sheet of a string as a quantum field theory in 2 dimensions, where the fields are the spatial dimensions of the space-time in which the string lives. Okay, and so if you have just these x mu of sigma tau, it's a bosonic string theory, but it's necessary to introduce other internal degrees of freedom, such as spinors on the world sheet, which do not have a classical limit, and then you get super string theory. But essentially, a string theory is a sum over surfaces, and without interactions, you would sum over surfaces, or at least to leading order, you sum over surfaces which are of genus 0. So this is not a closed string, this is an open string, but you can, I mean, a sum of surfaces with genus 0 would be the leading order string theory, and you'll have punctures representing initial and final states of the string. But now the difference between string theory and quantum field theory comes in is that once you've defined how to do the sum.
Can I consider quantum field as a function from some space-time to operators on the Hilbert space?
Yes, you can consider it that the field is an operator on Hilbert space at each point in space-time.
And the point varies on the space-time or what?
I didn't understand the question.
No, I want to consider quantum field as a function between 2 sets.
Well, a quantum field.
Yes.
There is one way of thinking of a quantum field is an operator at each point in space-time.
Yes. So.
Okay. I mean, then you will calculate expectation values of these operators.
Yes, that's right. But quantum field itself is a function from space-time to operators on Hilbert space.
Yes. Okay, and now in contrast, a world sheet of a string, you have a function from a 2-dimensional parameter space parameterizing the world sheet of a string, 2 operators which describe the location of the string in space-time. So now here, the space-time gives you the fields. So x mu runs over d dimensions. So in fact, in like 10-dimensional string theory, mu goes from 0 to 10. But it's a function from the 2-dimensional world sheet to these 10 different operators. So 10 different functions from 2 dimensions.
And how does the count 10 comes up?
Well, you're asking why the number 10?
Yes.
So I mean, it comes from consistency.
So for space-time.
Okay, I mean, here mu goes from, no, so mu, so you choose the number of dimensions of space-time. Okay, hypothetically, I mean, if you had a string theory in 4 dimensions, then x mu can run from the 4 dimensions of space-time.
No, but the number 10, or I heard this numbers.
Yeah. So why does it come?
So it's some fiber bundle on space.
No. So space-time, literally, instead of like we see 4 dimensions, 3 space and 1 time.
Yeah.
But if you want this sum over world sheets to be consistent.
So it's some Calabi Yau manifold as a fiber.
Well, it's not specified at this stage. You can just have the idea is you have 10. String theory makes sense in 10 space dimensions, 10 space-time dimensions.
I just want to see how that 10 comes out. So if Calabi Yau is 3-dimensional, the complex 3-dimensional.
Well, it's more the other way around. That you string theory is 10-dimensional. Now, if you want to get to a 4-dimensional space-time, you have to choose 6 of those dimensions to be compact. And the natural choice is to make them a Calabi Yau manifold. So 6 real dimensions or 3 complex dimensions. But the fact, why do you get 10? It comes from the mathematics of this sum over world sheets. And it's slightly subtle. So I won't
Yes.
really be able to describe it here. But so the claim is this is a sum over paths. So it's a sum over Riemann surfaces. Generically, the sum will not be consistent. It's not going to be well defined. But under special circumstances, you can find a way that it's well defined by physics standards. It's probably still not by math standards. And then in that case, space-time has to be 10-dimensional.
This Riemann surface is non-compact in general, because only Riemann surface of genus 0 is unique, compact. But non-compact are many Riemann surfaces of genus 0.
Yeah, so we do consider punctured Riemann surfaces.
Punctured Riemann surfaces, punctures can be 3, 4, 5.
It depends on, so if you're scattering 2 particles in and 2 particles out, you'll have 4 punctures. If you're if it's 1 particle in and 1 particle out, just propagation of a particle, there's just 2 punctures.
If m particles and
so the number of punctures is the number of incoming and outgoing particles.
okay.
Okay, and so unlike quantum field theory, once you've defined the sum over paths for non-interacting strings, there's no freedom to choose interaction vertices. Interaction vertices just means you're having a sum which includes surfaces of non-zero geoms. Okay, so in some sense, interactions are uniquely defined in string theory. They're not a choice like in quantum field theory. Although there are different ways of doing a sum over genus 0 Riemann surfaces, but once you define that rule, it tells you how interactions are held. And now, while it was impossible to include gravity in quantum field theory, in string theory, gravity is just emerges from the sum over world sheets automatically. Okay, and this is just a statement. Okay, but in order for the sum over world sheets to be well defined and consistent, there are 2 features that sort of string theory has to have. First, you require that there has to be an additional symmetry relating bosons to fermions, known as supersymmetry. I'll try to talk about that a little bit more. And we also require space-time in which the strings live to possess exactly 10 dimensions. Okay, some of those dimensions can be compact, like a Calabi Yau manifold, or you can study, just theoretically, you can study strings propagating in just 10 flat dimensions, space-time dimensions. Okay, when subject to these constraints, there are 5 different superstring theories one can define. Okay, and the allowed vibrational modes of a superstring correspond to different particle states, and they transform as different representations of the Poincare group, or the Poincare algebra. The lowest energy modes.
Poincare algebra is 10-dimensional?
Yeah. Yeah, the 10-dimensional Poincare.
It is conformal. It is what is it as a loop as a Lie algebra? Is it SO 4,2 or something? 4,1?
I didn't hear the question.
The Poincare algebra as a Lie algebra.
Yeah.
Is it SO 4,2?
No, so it's a non-compact.
Yeah.
Yeah, it's. I'll write down. So we'll write it down later. I mean, I'll show you that this is the Poincare algebra. So you have the algebra of SO 1, D, which is mu nu. These are the generators of SO 1, D, and you also have another generator P mu, which generates translations, and that gives you the Poincare algebra. So it's a semi-direct product of translations and rotations.
Yes.
Okay, so the rotations are SOD -1, 1, but the translations are just, there are this generator P mu, and
The rotations and translations is the affine part, right?
translations is the affine part, and
Rotations
rotations.
and translations together will form the affine part. But there is a further conformal compactification or something.
No, so there's also a thing called a conformal group.
Yes.
But in space-time, we're not getting the conformal group. Sorry. Okay, I mean, we're just getting the Poincare group. I mean, yeah, and that's, yeah, sorry. That's the, yeah, in space-time, we get the Poincare group, we get a supersymmetric version of it, but I'm not.
Okay.
And then it's a local symmetry because there's gravity. But at first approximation, just to understand what are the particles, you just think of them as representations of Poincare. You can add other generators if they're there, but okay. And the lowest energy vibrational modes correspond to a finite number of massless particles, one of which is always a graviton. Then higher vibrational modes correspond to an infinite tower of very massive particles. So in the low energy classical limit, we have only the massless particles of string theory. And this low energy limit defined these 10-dimensional versions of Einstein gravity known as supergravities. Okay. And it also turns out that superstring theories contain extended objects known as D-branes. And these are defined by, okay, if you allow strings to be open, then you have to put consistent boundary conditions for these strings. And the allowed consistent boundary conditions for open strings on surfaces on which they end define D-branes. In the supergravity limit of superstring theories, D-branes can be thought of as charged black brane solutions, i.e. sort of black holes, but they're p-dimensional instead of zero-dimensional, that preserve some fraction of the supersymmetry. Okay, so as I said, the string theory, to make sense, has to be a 10-dimensional space. So if you want to reproduce the real world of 4D physics, you might consider string theory on some background. Say R9 minus D1 times MD, where M is some compact D-dimensional manifold. And sometimes that manifold can be a Calabi Yau manifold of 6 real dimensions. Or it can be sometimes other manifolds. You might study, and you might even study string theory on ADS4 across CP3 or some other backgrounds. But the manifold itself is a geometry, and its metric must satisfy Einstein's equations and some other equations for the fields on the manifold. So that restricts the manifolds to some level. Okay, and then there's the notion of duality, which we'll come to. And okay, sometimes different superstring theories on different manifolds are physically indistinguishable from each other. Okay, and when you consider the dualities between the different string theories, it turns out that it's consistent to postulate that the 5 string theories are different limits of another theory, which happens to be 11-dimensional and is called M theory. So this is a list of the 5 different string theories, and yeah, it turns out M theory has another classical limit, which is 11-dimensional supergravity. Okay, so that was the rapid sort of introduction to string theory. And here now, next, I'm going to tell you what is the field content of 11-dimensional supergravity. Okay, so to tell about the field content of 11-dimensional supergravity, let me just review some basics about the representations of the Poincare group. So the Poincare group, as we discussed, is a semi-direct product of translations in d-dimensional space-time, and the Lorentz group, which consists of rotations and Lorentz boosts. Or if you want, you can just get rid of the minus sign and just consider SOD, and that's just the rotation and translation. So some fields, such as bosonic fields, they form unitary representations of the point gray group. Other fields, which are fermionic fields, form projective unitary representations of the point gray group. And the different representations were worked out by Wigner some time ago. I'll just sketch how they were described. So the generator here's the point gray group's Lie algebra. So you have
the electromagnetic fields is fermionic, right?
No, the electromagnetic field is bosonic. So E and B.
Bosonic, I see.
Yeah, the electron is fermionic. So the electron is a particle, but in quantum field theory, it corresponds to a field. So the field of the electron is fermionic. The field of the photon, which is the electromagnetic particle, that's bosonic.
So the photon is bosonic, yes.
Yeah. Okay, so this is the Lie algebra of the point gray group, and we want to find representations of it. So first, to handle the generator P mu, we represent the momentum by a number which is K mu, which has whatever dimension we're in, D components. And the inner product of K mu with itself is invariant under Lorentz transformation. So its value is sort of an invariant, and we can distinguish between representations where K mu, K squared is equal to 0, and representations where it's not equal to 0. So we can distinguish between massless and massive representations. And in supergravity theory, we need to focus only on massless representations.
Because the photons have no mass.
Right, photons have no mass.
And similarly, which other elementary particles have no?
In principle, the electron also is massless, and it acquires its mass through interaction with the Higgs.
Electron is massless. Oh.
Well, theoretically, you describe it by a field which is massless. Two fields, a left-handed and right-handed field, and they both have to be massless. But because they interact with the Higgs at low energies, it looks like it's massless.
I read that the electron has roughly of the size of.
So at low energies, the electron has mass. But at higher energies, it's a massless particle whose mass sort of arises from interaction with another field called the Higgs boson field.
Yes.
Okay, so really you can think of every field is practically massless. Of course, there are gauge bosons for the nuclear force, which are massless. The graviton is massless. Okay, here we're looking at, of course, 11-dimensional supergravity, which is just a theory. It might be related to the real world. It might not be. All the fields in that theory are massless. Okay, and even the fields of the standard model have such small masses that, from the perspective of string theory, you consider them massless to begin with. Okay. So first, you can use a Lorentz transformation to convert K mu into a particular form. Okay, this, say, it's some value for K0 and some different value for K1, and the rest of the entries are 0. And this preserves the condition K mu equals 0. Okay, here I'm using Einstein summation notation. Right? Okay, the residual subgroup of the Lorentz group that preserves the above condition is SOD minus 1. Or actually, this is SOD minus 2, sorry, because we were considering SOD minus 1. So this is, well, if D is the number of spatial dimensions, then it's SOD minus 1. If D is the number of space-time dimensions, it's D minus 2. So it's technically a typo. And to specify a representation of the point gray group, we must specify how the field transforms under SOD.
SOD minus 1 is a compact group.
Yeah, now it's a compact group. It's just the rotational group. And this is actually a typo. This should be D minus 2. Sorry.
So the
Because
irreducible
these
representations
two are, yeah, so just rotations that amongst these last three.
so irreducible representations are discrete
Yeah,
and finite dimensional and just certain their dimensions are just certain integers.
right,
Yes.
right. So, yeah, so all the continuous stuff is kept in K, and this rest of it is discrete. Okay, so essentially, what are the representations of so D minus 1 or 2? Or so they say D minus 1. So first, there are scalars, which is the trivial representation. So a field which is a scalar is said to be a spin 0 field. Okay, which this terminology comes from 4 dimensions, but we use it in higher dimensions. Then you can consider a symmetric traceless tensor of any rank, and that'll transform under rotations as an irreducible representation. And these are said to be of spin R, where R is the rank of the tensor. Okay, and the third representation is you can have an anti-symmetric tensor, and then the rank must be less than the dimension.
What does physically spin R means?
Well, if it's rank 1, then that's spin 1.
Yes.
And that would be a photon.
But R can be.
If it's rank 2, then it's a spin 2 particle, which is a graviton. Higher spin particles are not observed beyond that in nature as elementary particles.
Oh,
so really we are only concerned with rank 1 and 2 for massless fields.
So physically, the symmetric traceless tensors of rank R equals 0, 1, and 2.
These are the ones that count for massless fields. But okay, theoretically, we can also consider theories with higher spin fields. And string theory does predict there exist higher spin fields, but those are not massless. Those have a very large mass. Okay, so from the point of view of massless fields, we will consider only R rank 2. Okay, and the third type of representation is an anti-symmetric tensor of some rank. And of course, the rank must be less than the total dimension, otherwise it would vanish. Okay, and these are spin 1. These are not spin 0. That's another type. Okay. Okay, so these are the representations of the point gray group, and these are the different. So these tell you the different bosonic particles you can have in a field theory. There are also projective representations of the point gray group, and we can construct them by the following construction. So let gamma mu be some n cross n matrices, which are known as gamma matrices, that satisfy the following relation. So here, this squiggly bracket denotes the anti-commutator, and we say that the condition is that gamma mu plus gamma mu equals 2 eta mu. Okay, then if you have any such matrices, you can show that the commutator of these two matrices, that is gamma mu minus gamma mu, satisfies the same commutation relations as m mu, and hence furnishes a representation of the Lorentz group's Lie algebra.
So what is gamma n mu?
That should have been gamma mu. That's a typo.
Oh, sorry.
Sorry, yeah. Yeah, so this also works. Okay, so this is one way to get a representation of a point gray group, but the representation you get is projective. So if, for example, if you do a rotation by 360 degrees, you'll get a minus sign. So it's not a global representation of the Lorentz group, but it's a representation of the Lie algebra. Okay, and these happen to be physically realized. So the wave function of an electron, it picks up a minus sign if you rotate it by 360 degrees. Okay, so one can explicitly construct matrices satisfying this relation using tensor product of the Pauli matrices. So that's sigma 1, sigma 2, and sigma 3 these are the Pauli matrices. And if you, for example, in D equals 3, you can simply use these matrices themselves if you want gamma matrices for SO3, or you can include a factor of I for one of them, and it gives you gamma matrices for SO2 comma 1. If you want to do higher dimensions, the way you construct it is you simply carefully take tensor products of these matrices with each other and with the identity matrix, and that gives you gamma matrices which satisfy this equation. But okay, when you do this construction, you find the dimension of the gamma matrices depends on the number of space-time dimensions, and it goes as 2 to the floor of d over 2. So for example, in 4 space-time dimensions, gamma matrices are 4-dimensional. In 11 space-time dimensions, gamma matrices will be 32-dimensional. Okay. Okay, and then so let me write the matrices gamma mu, and alpha and beta are the sort of the internal indices. Mu tells me which gamma matrix you're in. So there's sort of 2 different sets of indices. So alpha and beta go from 1, 2 to n, and mu goes from 0 to d. So you have a field psi which is acted on by these gamma matrices, and it has n components, and it'll transform under Lorentz transformations using the commutator of 2 gamma matrices as m mu nu. So that sort of field is what we call a spinor, and it's called a spin 1/2 representation of the Lorentz group. Okay, in general, the entries of this field psi must be complex, in which case psi is said to be a Dirac fermion. But in some dimensions, and it really depends on D mod 8, it's possible to choose purely real gamma matrices, in which case we can also restrict the field psi to be real, and then psi is said to be a Majorana fermion. Okay, in some other dimensions, or sometimes same dimension, we can also define a matrix via the product of all these gamma matrices with some factor of I. And this product of all the gamma matrices is invariant under Lorentz transformations. So it's sort of a Casimir, and then you can use this to distinguish a general Dirac fermion into 2 different representations. One which this has eigenvalue +1, another where it has eigenvalue -1. And such spinors are called Weil spinors.
Hi, Professor Prakash. So, is in 1D, do we have Majorana? I mean,
I think in one spatial dimension or one space-time dimension.
It's one space-time dimension.
Yeah, I think in one space-time dimension, then you just have a single dimension, and you can have a real fermion or a.
So the Dirac fermion does not have a spin, or do they have?
They do have spin. They're just so here the way I mean so there's a. I mean, the word Majorana fermion also arises in topological quantum computing and stuff. Here, the real only thing that matters is that, I want to find matrices that satisfy this anti-commutation relation. Okay, and the way I do that is I take tensor products of the Pauli matrices. Now, is it possible to choose them in such a way that all the entries of capital gamma mu are real? So that means if I multiply sigma 2 by I would get 0, 1, -1, 0. And I could use that for gamma 0. And then gamma 1 I can take to be sigma 1, and gamma 2 I can take to be sigma 3. And now that's a purely real representation for SO2 comma 1. So if you can choose them Dirac matrices to be all real, then you can, then that means when you do carry out rotations, if your field psi was real to begin with, it stays real. And therefore the irreducible representation is a real, I mean.
Majorana was a physicist, right? Is his name.
Yeah, I think he was a physicist. He might have been a mathematician, I'm not sure.
What did you do?
Of course, Dirac came up with, gamma matrices, so we know what Dirac is.
Right.
Majorana, I mean, I use the name, this is the name that's used, this is the definition given, but I've never heard too much about Majorana. I mean, maybe other people know about him. Maybe I should know about him, but it's the name Majorana fermions is used for real representations, but yeah, I don't know I've never seen Majorana's name elsewhere. So maybe someone who knows more will be able to do this. And then there are also these spinners called Weil spinners, and here these spinners can have a chirality. So there's a difference between a left-handed spinner and a right-handed spinner. Okay, and the way to see that is, if you have a particle traveling at the speed of light, then you can never go to its rest frame because you can't travel at the speed of light. So there's no observer who can go into its rest frame. And then that means if it has angular momentum counterclockwise to its direction of motion, it would be counterclockwise for all observers. Similarly, if you have a particle who's moving and its angular momentum is counterclockwise to its direction of motion, that would be counterclockwise for all observers. So there's a sense in which you can have, if you have a massless particle, it can be either left-handed or right-handed. Okay, and in fact, in nature, it happens. The electron, there's a left-handed electron, which is massless, and a right-handed electron, which is massless, and they both have different charges under the weak force. So in this sense, nature sort of breaks parity and distinguishes between left clockwise and counterclockwise rotation relative to the direction of motion. Okay, so from the spinner representation, you can define other projective representation by taking tensor products of the spinner representation with itself and then decomposing it into a sum of irreducible representations. So in particular, there's a representation which is the tensor product of a vector with a spinner. That is a rank one representation of the non-projective Lorentz group with a spin 1/2 representation. It's not, if you just take this tensor product, it's not irreducible, but it's proportional to the direct sum of just a spinner, a spin 1/2 representation, and another representation called the spin 3/2 representation. And we denote this by a field called the Gravitino or Rorita-Schwinger field, which is psi mu alpha. So here mu goes from 0 to d minus 1, and alpha goes from 1 to n. N is the dimension. Okay, so this is another projective representation of the Lorentz group. So that there's a bit fast, but the point is you can look at all the representations of the Lorentz group. Some are projective, some are not projective. Those which are in projective representations are called fermions. And those particles which are not in projective representations, they're just in conventional representations of the Poincare group, those are known as bosons. So of course, bosonic fields and fermionic fields are both operators acting on a Hilbert space in quantum field theory. But you can also consider classical field theory, a classical limit of this quantum field theory. So in the classical limit, bosonic fields are described by real or complex numbers. But the classical limit of fermionic fields, they're described by these sort of formal anti-commuting objects known as Grassmann numbers. And this sort of originates from the Pauli exclusion principle. Okay, and another difference between bosons and fermions is that bosons obey second order differential equations, while fermions obey first order differential equations. Okay, finally, there's a symmetry called supersymmetry, which relates bosons to fermions. So it can be thought of as an extension of the Poincare algebra to include an additional generator, which is conventionally written as Q. And these additional generators obey anti-commutation relations instead of commutation relations. So what you get is known as a Z2 graded Lie algebra. So of course, in the Lie algebra, you have this Lie bracket, and it's just an abstract bracket. But in practice, it comes from the it obeys all the relations like the Jacobi identity, which follow from the fact that it could be a commutator. So in a Z2 graded algebra, you have two brackets, one with square brackets, one with squiggly brackets, and the squiggly brackets obey relations that an anti-commutator would obey. So one of the necessary conditions for a theory to be supersymmetric is that the number of bosonic degrees of freedom should equal the number of fermionic degrees of freedom. Okay, and the detailed form of the supersymmetry algebra is very dimensional dependent, because spinors and gamma matrices are dimension dependent, and so are the representations. Okay, so here, this is the supersymmetry algebra in 11 dimensions. So in addition to the usual generators of the Lorentz group, we also have this generator Q, which is the generator of the supersymmetry algebra, and S is the commutator of two gamma matrices. And so Q transforms as a spinor, and its commutator of two Qs gives you essentially a momentum times the gamma matrix. So roughly, this is the supersymmetry algebra. So if you're looking for supersymmetric theories, it's actually difficult to find them in larger dimensions, because we saw the dimension of gamma matrices increases exponentially with dimension, which means fermionic fields, even the smallest fermionic field, spin 1/2 field or spin 3/2 field, its degrees of freedom will also increase exponentially. Whereas bosonic degrees of freedom for fields of spin less than 2, they increase quadratically with dimension. So as the dimension increases, it's sort of harder and harder to define a supersymmetric theory. So it turns out that the largest dimension of space-time in which you can have a supersymmetric theory with no fields of spin greater than 2 is 11. So basically, if you like extra dimensions and supersymmetry, then 11 is the maximum number of space-time dimensions. And this was known from the late 70s. And it turns out there's a unique supersymmetric theory in 11 dimensions, which is known simply as 11-dimensional supergravity. And it turns out that, okay, this is a classical theory, but we now have reason to believe that there exists a quantum theory whose classical limit is 11-dimensional supergravity, and that's what we call M theory. Okay, so the question is, what are the fields of 11-dimensional supergravity? So the fields are actually very simple. There's just 3 fields. There's a graviton field, G mu nu, a gravitino field, which is like the fermionic superpartner of the graviton, which is psi mu alpha, and a 3-form gauge field, C mu nu rho. So I'll discuss each of these 3 fields in a minute. So the graviton is a massless spin 2 particle in 11 dimensions. So its physical degrees of freedom form a symmetric traceless rank 2 tensor under SO9. So basically the construction I gave, it'll be a representation of SO9. So the number of degrees of freedom in its symmetric traceless rank 2 tensor are basically 9 times 9 plus 1 over 2. That's a symmetric tensor, rank 2 tensor, or symmetric matrix that of 9 cross 9. And then you subtract 1 because the trace is 0. So that comes to 44 degrees of freedom. So these are 44 bosonic degrees of freedom in the spin 2 graviton field of 11-dimensional supergravity. Now, in the supersymmetric theory, the graviton must have a fermionic superpartner, which is the Rorita-Schringer spin 3/2 particle, and that's denoted as psi mu alpha. Here, mu is a vector index and alpha is a spin index. Now, as I said, gamma matrices in 11 dimensions are 32 dimensional. So the total number of degrees in freedom of a vector times a spinor would be 9 times 32. But you divide by 2 because fermionic fields obey first order differential equations, so that the degrees of freedom are reduced by 2. So you would have 11 minus 2 times 32 over 2, but because there's also spinor representation, we subtract 32 over 2 from that, and finally we come out with 128 degrees of freedom in the rotary Schrödinger spin 3/2 particle. So we had 144, we had 44 and 128 degrees of freedom. What happens for the remaining 84 bosonic degrees of freedom? So the C mu nu rho field is an anti-symmetric rank 3 tensor under SO9. So its degrees of freedom, there's 9 times 8 times 7 over 3 factorial possibilities for the different indices, and that corresponds to 84 degrees of freedom. These are bosonic degrees of freedom, and now we see that the bosonic and fermionic degrees of freedom in 11-dimensional supergravity match. Of course, equal number of bosonic and fermionic degrees of freedom is not sufficient for supersymmetry, but it's necessary. So now let's talk a little bit more about this 3-form. So the 3-form is basically a P-form field, which is a totally anti-symmetric rank P tensor. And given a P-form, you can define another P+1 form by its exterior derivative. And of course, D squared equals 0, and the exterior derivative doesn't depend on the metric. So this 3-form gauge field is sort of analogous to the 1-form gauge field, which describes electrodynamics in our world we live in, which is formed by the scalar and vector potential phi and a vector A. So 2 3-form fields, that means which differ by a gauge transformation, which is the derivative of some 2-form lambda of x, are physically indistinguishable. So in fact, they're equivalent. However, the field strength, which is a 4-form formed by taking the exterior derivative of the 3-form, is gauge invariant, and that's physically observable. So it's analogous to the electric and magnetic fields of electromagnetism. Okay. Now, if you have a 4-form, you can sort of integrate that along a 4 surface, such as S4. And this is analogous of calculating the flux of the magnetic field through a sphere if you do the same calculation in the world we live in. So such an integral will give you a non-zero answer. If such an integral has a non-zero answer, then it implies that there exist magnetically charged objects in theory. So if you have a magnetically charged object, which you can surround by an S4, and it lives in 11 dimensions, then its world volume must be 6-dimensional, which means it's a 5 spatial dimensional object, and that's called an M5. So from the presence of the 3-form gauge field, we learned that M theory contains these 5-dimensional objects called M5 grains, and they're sort of magnetically charged in this supergravity. Okay, we can also define the Hodge dual of a P-form, which is a D minus P form, and that's defined as follows. And the Hodge dual interchanges electric and magnetic fields. So the Hodge dual of the 4-form field strength is a 7-form, which we call H tilde7. So H7 can be integrated along a 7-dimensional surface, such as S7. And this is analogous to calculating the flux of E.
Why do you call magnetically charged? Is that the same as electromagnetically charged, or is it?
It's analogous to electromagnetically charged.
But you're saying only magnetically charged.
So are you asking why did I say M5 brain?
Yeah,
is
why the
magnetic?
terminology? Why not EM charge rather than magnet specifically?
Okay, well, the point is, so of course, the distinction between electric and magnetic is sort of arbitrary, but it's conventional to choose,
Yeah,
one as electric and the other as magnetic.
yeah.
You can argue that which is electric and which is magnetic is an arbitrary choice, but the point is, the fields which, so if you integrate the H4 along a four-dimensional surface, we call the charges that create that flux as magnetic charges. The charges which, if you integrate the Hodge dual of that field strength along a seven-dimensional surface, the charges which create a non-zero value for that integral we call electric.
Is this any way connected with this search for magnetic monopole?
Yes. So in four dimensions, electromagnetism is described by a one-form field.
Yeah.
So the field strength is a two-form, and its dual is also a two-form. So in four dimensions, magnetic objects and electrically charged objects are both point particles.
Are
Point particles in four dimensions.
point particles now.
Okay, but in 11 dimensions, if your gauge field is a three-form, the argument is electrically charged objects have to be two-dimensional objects, and magnetically charged objects have to be five-dimensional. Okay, so it's not like, so the fact that electric charges are point charges and magnetic charges are point charges is due to the fact that electromagnetism is a one form in four dimensions. Okay, if you have a three-form gauge field in 11 dimensions, then the dimensions of magnetic and electric charged objects are different, is what I'm trying to argue. Is that roughly clear, or it's?
Yeah, I understand. Sort of.
Yeah. So the point is that if you're going to integrate calculate Gauss's law for a field strength of a three-form, then you have electrically charged objects which are M2 branes by this argument here. Okay, because a seven form can be integrated along a seven-dimensional surface. So if you have an S7, then including the radial direction, it's like an electric object has 7 + 1 transverse dimensions, which means its world volume is 11 - 8 = 3 dimensions. And this is the world volume traced out by a two-dimensional membrane called an M2 brane. Okay, so these are the objects in M theory. So earlier we talked about string theory. So string theory had one-dimensional objects. M theory does not have one-dimensional objects. It has two-dimensional membranes and these five-dimensional M5 branes. And that's it. So this is the summary of M theory, is that it contains three fields: the graviton, the gravitino, and the three-form gauge fields. It also contains two-dimensional objects and five-dimensional objects called M2 branes and M5 branes. This we discovered from studying the low energy limit of M theory, but it's a theorem that if you have a state preserving a fraction of the supersymmetry, which M2 brane and M5 brane states would preserve, you can argue that it's protected, and just by representation theory, it continues to exist when the interactions are strong. So in other words, these also appear as central charges in the 11-dimensional supersymmetry algebra. So even when interactions are strong in the quantum theory, M theory contains M2 branes and M5 branes, and it doesn't contain strings. So that's the introduction to M theory. So I think I'm now out of time. It's 8.
Yeah.
So
you would like to continue some other day? It was interesting talk.
it depends. I mean, I can try to quickly sketch the remaining things, or I can stop now, or I can continue another day. Either way.
Another day would be better.
Okay, so that's fine. If there are any questions on what I've covered, I can answer any more questions.
More time to prescribe.
Okay, so that's great. So this was M theory, and the remaining stuff was a little bit about how you get the other string theories from M theory, and that's it. So thanks a lot for giving me the opportunity to speak. I enjoyed the lectures that I've seen, particularly the introductory lectures that we had from Professor from ISC Bangalore and some of the other lectures, and thanks a lot for giving me this opportunity.
Okay, we will decide another date. And Utkarsh, are you there?
Yeah, so thank you very much for a very nice talk. It was really great to hear you. So if we have any questions or comment.
Sure. Is there a way that Majorana and Dirac fermion like interchange? Like for example, neutrinos usually behave as like Dirac and Majorana, right? So like is like physically can it behave in one form at one point of time, and like in another point of time it can behave in another form?
No, I mean in principle a Dirac fermion is just mathematically it's a complex vector of n dimensions that the gamma matrices act on, whereas a Majorana fermion will be a real vector. So you have two Majorana fermions can be combined to make a Dirac fermion, just like two real numbers can give you a complex number.
Oh, okay. So like it can give a real if they both Majorana fermions combine. In that case,
so two Majorana fermions can combine to a complex Dirac fermion, and whether it makes sense to treat them as two Majorana fermions or just a single Dirac fermion can depend on the circumstances.
Oh, okay. Thanks.
Can I ask a question about the standard model?
Yeah.
Quarks are connected with the non-projective representations, right?
Yeah, they're also spinors, spin 1/2.
They're connected with the non-projective representations.
Yes. So quarks are also fermions, and they're projective. Sorry.
Fermions are projective.
Yeah, no, quarks are also projective. So if you rotate a quark by 360 degrees, its wave function gets a minus sign.
But
I misanswered your question. So your question is quarks.
I have the three quarks that I wondered, and
there are three quarks each. So the quarks, there's an internal symmetry rotating the quarks together, which is nothing to do with space-time. Okay, so you can have three different fields and you can sort of interchange them and get a symmetry. But that's nothing to do with the space-time dimensions. If you just take a single quark and you rotate it in space, just physically rotate it by 360 degrees, its wave function gets a minus sign. So that means it's a projective representation of the Lorentz group. Yeah, of course, you can have other symmetries, like if you have 5 different fields in your theory, and they're all obey the same laws, then there can be an SO5 symmetry rotating them amongst themselves. But that SO5 might have nothing to do with space.
But I think for the standard model, the group is SL3C, right?
So there's different groups. The gauge group of the standard model is SU3 times SU2 times U1.
But what was it, the 8-fold way, that 8 corresponds to the dimension of SL3C.
SU3. Or yeah, but that, or it could be SL2. SU3's Lie algebra is 8-dimensional.
Right, and its complex replication is SL3C.
Yeah, but that is
the standard model.
Yeah, but okay, this So SU3 comes in two different ways. I mean, one thing is you have three quarks whose masses might be approximately the same. So now you can sort of rotate them amongst themselves, giving you an SU3 symmetry.
But you know, the Lie group corresponding to this SU3 algebra, there are two Lie groups. One is simply connected, the other is not.
Right. So under this SU3, as far as I know, it's the simply connected. It's a non-projective representation of this SU3.
So that is non-projective representation.
But quarks also transform under the Poincare group separately. So there's there's several groups. So there's this SU3 and there's also the Poincare group.
So can you make a statement about quarks just in the SU, restricted to SU3?
Yeah, then it's a non-projective representation.
Yes.
Okay, but that's not the space-time symmetry.
Okay.
Yeah. So, but as far as Poincare group goes, it's projective. Okay.
So how does the standard model connect with the string theory?
Well, it doesn't yet connect, but the idea is you take one of these 10-dimensional string theories. If you put 6 of the dimensions to be a Calabi Yau manifold, then the different topological properties of the Calabi Yau manifold and the geometric properties, such as the Hodge numbers, these will tell you what are the low energy fields of the 4-dimensional theory and their interactions.
But would you say that the standard model is not a restriction of the string theory?
No, I mean, it's quite possible that it is. It's just a question of finding the right way of compactifying string theory.
Yes.
To get it is very difficult. But like there's many ways of compactifying string theory. So it may be there's a billion ways or 10 to the 100. So finding the way which matches the standard model might be extremely difficult, but it's certainly conceivable. You can get theories which look like the standard model without much difficulty.
You could embed SU3 in SO6.
Yeah, so there's various ways of getting any given ingredient in the standard.
Yes.
If you want to get everything right, that's difficult. But if you want to get some features, you can get those features pretty.
Does SO6 play a role in string theory?
SO6
or SO5, SO6?
Well, it can play a role in string theory. I mean, SO8 plays a role in M theory because of triality and.
Yes, that is triality. Yes.
Okay, and SO6. I mean, it can play a role. I mean, any group, any SO group, there are solutions where those enter. So I mean, there are solutions with SO6 symmetries.
Okay, thank you.
Okay, thanks.
Oh, thank you very much again. So if we don't have any more questions and comments, so let's thank the speaker and end our today's session. Thank you very much.
Thanks, Utkarsh, also for sharing the talk, and thanks, Shiroman.
Yeah. Thanks.
See you once again, maybe next month.
Okay.
Bye. Good night.
Yeah,
Bye.
bye-bye.